You play a game where you sum independent, identically distributed, uniform random variables over the interval 0, 1. The first time the sum exceeds 1, record the count of needed variables. What is the expected number of variables? A standard game would unfold something like this. One initial observation, the number of variables, n, takes positive integer values greater than 0. Most of the time, when faced with the duty of computing the expected value of n, we would find the probability that n equals a particular integer k. Unfortunately, in our case, this is hardly a straightforward task, and I wholeheartedly commend you if you try and do it, since it looks like computing the individual probabilities is rather arduous. How can we proceed from here? Let's start by writing the formula for the expectation of a discrete random variable. Splitting I times the probability that n equals I into a sum of probability that n equals I counted I times, and aligning the values as seen on the screen, we can rewrite the expectation as the sum over the observed columns. The preceding sums, excluding the first, which is equal to 1, are respectively equal to the probability that n is greater than k for each k between 1 and infinity. Are these probabilities easier to compute than the ones we have been avoiding? Truthfully, this does not appear to be the case, but you will see how we get out of this situation. Until now, we ignore the definition for n. It becomes useful when attempting to compute the probabilities above. N is higher than a given value k if the sum of the first k uniform random variables did not yet reach 1. We should start by investigating the results for small values of k, starting from 1. The probability that x1 is less than 1 can be drawn like this. The blue segment is the space of all possible values for x1, and the green highlighting is the space of all values of x1 less than 1. The conclusion is clear. The probability is 1. For k equals 2, the things look as follows. The square represents the space of all pairs of points x1, x2, and the triangle where the sum is less than 1. Naturally, the probability is 1 divided by 2. One last easy-to-draw case is in 3D. The triples of points lay inside the unit cube, and the tetrahedron in the corner is the space where the sum is less than 1. The result is the volume of the pyramid, hence 1 divided by 6. A new meaning for the probability that the sum of xi's is less than 1 starts to take shape. Let's quickly try and formalize it. For any positive integer k, the equation x1 plus x2 plus and so on plus xk equals 1 determines a hyperplane in R to the k. It splits the space into two subspaces and contains the point ai that have as its only non-zero coordinate 1 on the ith position. The inequality represents a simplex or a hyperpyramid in R to the k. The origin is its apex, and the k-1 polytope a1, a2, ak is the base. Now we have to compute its volume. If you already know the formula, amazing. Otherwise, there are a few ways to arrive at it. So, we have a set of points x in the hyperspace with a sum of coordinates less than 1 and each coordinate positive. We can employ the following one-to-one transformation. Change the point x to y with each coordinate yk equal to the sum of coordinates of x up until index k. The only condition that remains on y is that its coordinates are sorted and between 0 and 1. It's clear that the transformation is one-to-one, but the two shapes determined by the sets of points are not congruent. how do we know that the transformation preserves volumes? To assess the change between the 2 points, we use the Jacobian of the transformation. Now, it's time to look closer at the matrix and make sure that it's clear how we arrive at it. Since this is a lower triangular matrix, the determinant is equal to the product on the diagonal, namely 1. This means that the ratio between the volumes is 1, and we can proceed with computing the volume of the set of y's. Up until now, it looks like we have been running in circles, exchanging sums of random variables for points in hyperspace and then moving those points around. One more step, and we can hope that everything falls in place. Take the k-dimensional hypercube. For any point, there is exactly 1, up to some equalities, ordering of its elements. In this case, I1, I2, I3, and so on, is a permutation of 1, 2, up to k, of which there are k factorial, all equally likely. Each set containing all points with elements in one particular order has the same volume. Naturally, this is a trivial observation, the proof of which is left to the viewers. Given that the sets are disjoint, the sum of their volumes must be 1. So, the volume of the set of points y that meet the condition 0 is less than or equal than y1, less than or equal than y2, and so on, less than or equal than yk, less than or equal than 1, is 1 divided by k factorial. Subsequently, following the chain of equalities, the probability that n is more than k is 1 divided by k factorial. Now, back to the initial question. The expectation of n is 1 plus the sum of 1 divided by k factorial, which is e. As usual, there remains the brutal way to solve this problem. Simulate it. Thank you to the Patreons supporting this video, and thank you for watching. If you enjoyed this and would love to see more, like this video, subscribe to the channel, and hit the alarm bell to get notifications when new videos are released. Leave any comments about this problem in the box beneath the video or on the dedicated webpage. For more info and other materials, please check the description box. See you next time!